All right, so the next example is the derivative of log 3x squared dx. So whenever possible, of course, we want to simplify these problems. And here, this is no exception. You can see what's happening is that we can take advantage of one of our logarithmic properties to simplify this a little bit. Just a quick reminder, as we saw yesterday, if you have something like this, log of, let's say, a to the r power, can be rewritten as r log a. And in a lot of cases, that will really make things a lot simpler for us. It's not necessary, but here, what I'm thinking about doing is rewriting this then as the derivative of 2 times log 3x over dx. Now remember, with a log, whenever we have the log of g of x, the derivative is going to end up being g prime of x over g of x. Okay, so by simplifying the logarithmic expression in the first place, that will probably make it easier to calculate g prime of x. So let's see what happens here. Let's allow g of x to be the 3x. Okay, so you've got the log of 3x. And then that implies that g prime of x is 3. So given that we know that our result will be g prime of x over g of x, the 2 has been moved out here. And so we've already calculated that g prime of x is 3, which goes in the numerator. 3x is our g of x. And so when we're done, we end up with 2 over x. So we basically did two things at once. We simplified the expression with the properties of logarithms, and then we calculated the derivative using the chain rule, which is specifically meant for logarithms. In other words, when we have the derivative of log of g of x, we end up with g prime of x over g of x. Okay, here's another one. Now, why don't we try this? Let's try letting u equal x squared plus 4. Then du dx would be 2x. And then du would be 2x dx. Do we have that? Almost. We need to provide a 2 here, which means we have to multiply the outside by 1/2. So we're going to end up with 1/2 integral du over u. So clearly this is going to wind up being a logarithm of 1/2 natural log absolute u plus c. And now we just simply substitute for u our x squared plus 4. All right, well, that was pretty straightforward. But again, obviously, if you chose the wrong u, you're going to end up with a messier expression than you started out with. But once you've got it done, you can see it's a very straightforward process. All right, and again, just reminding ourselves about logarithmic properties. It's often easiest to consolidate or simplify expressions using logs. Here's an example of something that looks like a nightmare, but in reality, it's not that difficult to combine these terms because all of these are powers of 3. Okay, for example, 9 is simply 3 squared. And then here, this can be rewritten as negative log 3 squared. Okay, and then the log of 1/3. Since this is the same thing as log 3 to the minus 1 power, we can leave it like that. Now, if you notice, all of a sudden, all 3 of these are powers of 3. So, and in fact, the first 2 are the same. I mean, they just drop out. So we have this. And this can be, you can leave it as log 3 to the minus 1. You could write it as log of 1 over 3, or you can leave it as negative log 3. Anyway, it's the same thing. But the strategy here was to take apparently terms that don't appear to have anything to do with each other and rearranging them by taking advantage of our logarithmic properties. And so all of a sudden it becomes clear that these two actually cancel each other out. So they're just left with this term. Also, don't forget the log base e. Remember, natural log is the same thing as log base e. So therefore, remember the log to base any b of b is just 1. So therefore, it stands to reason that the natural log of e is just 1. Because remember, this is log e, which means it must be 1. And of course, we just saw earlier in this chapter that we can find this graphically by looking at the area under the curve of y equals 1 over t from 1 up to e. Okay. So the area under the curve from 1 to e is equal to 1. And of course, we can also do the same thing with exponentials. Don't forget these important properties, e to the p. Now, the reason why we're able to do this, by the way, is because they're both the same base. Okay, this would be true for any numbers. You could have, for example, 2 to the p and 2 to the q, and you'd still have 2 to the p plus q. So the reason why we're allowed to use these properties is because in all these cases, we have the same base. When we do, multiplying them together like this means we can simply add the exponents. When we have a ratio like this, then we're subtracting. And this last case, which we have to be careful with, e to the p, where the entire expression is raised to the r power, equals e to the p times r, not plus r, times r. And that's because this expression means e to the p multiplied by itself r times. Okay, so in effect, you are using this rule. What you're actually doing is adding up p r times, which means p times r. In fact, when you come right down to it, both of these second and third rules are essentially taken from the first rule. They're not really 3 independent rules. They're all based on the same logic. But it's easy to remember things by having it written out this way. All right, now, the reason why this is important here is because all of a sudden a messy expression like this, which could get us involved with the product rule, doesn't have to be quite that messy, because if you notice, all of a sudden we can consolidate these exponents into something much more manageable. Now, we can certainly go ahead and use the product rule if you want, but I think you'll agree it's probably quicker to do it this way. Actually, we can just leave it like that. Now, you also recall that when we're taking the derivative of e to the g of x from the chain rule, we end up with e to the g of x times g prime of x. So here we're going to wind up with e, since this is all considered to be g of x, g prime of x, based on the power rule, would be 3 plus 2x. So this result will be e to the 3x plus x squared times 3 plus 2x. And you can rewrite it if you want. I mean, it's fine the way it is. Sometimes there are certain methods we like to use for organizing our results, but this is fine. So that, I think you'll agree, was a lot quicker than trying to use the product rule. Although you certainly can use it to double check if you want to. Now here's another one. Now here we may not need to bother with any rearrangements, because if you notice, if we let u equal minus x squared, then du dx would simply be minus 2x dx. We don't have minus 2x dx, but we're awfully close. Whoops, sorry, I wrote this wrong. Yeah, all we're missing is the negative. We do need to supply this negative. Other than that, we're good. Okay, so we'll have minus 2x e to the minus x squared times minus dx, which I'd like to rewrite just to gather together all the terms that we need so you can see better what we're doing. So it's clear that this is du, and this is e to the u. Okay, so remember, don't forget this negative on the outside, though. I almost forgot it myself. Yes, so by rewriting it like this, it's clear that you have e to the u times du by combining the 2x and the negative sign with the dx. So you just have, as you know, this is how we integrate e to the u. And we end up with minus e to the minus x squared plus c. Excellent. Okay. Now, how about this one? Oh my God. Now, this one requires us to use an identity. And, again, sometimes there are identities that will help us quite a bit with exponential and logarithmic functions. And here's one that may not be immediately obvious, but it turns out that as long as a is strictly positive, a to the x is the same thing as e to the x log a. How do you like that? Now, of course, why would this matter? Because if you have an integral of one or the other, you might find it easy to convert it to the other one, depending on which one, what situation you're in. It might make it easier to solve for your integral by being able to do some rearranging using this identity. Now, the derivative of a to the x, so just as a quick reminder, the derivative of e to the x is simply e to the x. Okay. Here, though, we have the derivative of a to the x. We need this extra constant log a. And we also, as we've already seen a few minutes ago, the derivative of e to the g of x is e to the g of x times g prime of x from the chain rule. And so here we have the same thing, except again, to this log a. And remember, no, you might remember that. The logic behind these rules is from this definition. Anyway, so let's use these. Oh, and here on the next slide, we have the corresponding integral functions. And again, I just would remind you that we have e to the x dx is simply e to the x plus c. And then here we have the two derivatives based on logs that are not based on e. And so these are the final results. And again, the only difference is this extra log a, this constant. Just like, remember this one, we just did this a few minutes ago. The natural log of g of x was g prime of x over g of x. So the only thing that's different now, because you have a different base, you have to provide this log a. All right, so finally, now when you see one of these, you're going to say, now in the past, what we've been doing is consolidating the exponents. And you might say this time we can't do that, but wait a minute. Wait a minute. I think you'll agree. Oh my God, look what we can do. We can make it simpler on ourselves by recognizing that 4 to the x is the same as 2 to the 2x power. And since both of these expressions have the same exponent, the same base rather, we can rewrite this as now this is still a bit of a mess. What we're going to do is go back and look at our rules. We have a, this is, remember, 2 is the base now, it's not e, okay? It is a, some a, which is 2 in this case. So it looks like we're using this rule. With a to the g of x, the derivative of a to the g of x. All right, so the original function was so that means clearly a is 2 and g of x is this exponent 2x plus x squared, which means that g prime of x, of course, based on the power rule, is simply 2 plus 2x. So we end up with a to the g of x, the original function, natural log of 2, and g prime of x, which is 2 plus 2x. Okay. And you might as well just leave it like that. I don't see any benefit from simplifying that. It's fine the way it is. Wow. So it's getting a little messy here. How about this one? So this is the log base A, some A, it's not E, obviously. So why don't we go consult with our rules, which, by the way, are in the book. It's just that they're all mixed together with all the other ones. At the back of the tables are back there with derivatives and trig functions. Those are integrals, sorry. The derivatives, yeah, yeah, here we are. That's right, they're using B's instead of A's. Whatever, it doesn't obviously matter, but they're here. Okay, so anyway, let's get back to it. And let's just revisit the rule that we need. This is the derivative of the log of some function of x. So it's log base A of g of x. And let's see, where did we? Here it is. It's this one. Okay. So let's use it. So therefore, what this is saying is that A is 8, g of x is 7x squared plus 4, which implies that g prime of x, based on the power rule, is 14x. So according to this rule, we're going to have 14x over 7x squared plus 4. And don't forget about this. We need the natural log of 8. Okay, so that's that. So it's not that hard as long as you recognize the correct rule that we're using. Now, here's one that's kind of intriguing, where we can approach it a couple of different ways. The derivative of 4 to the x to the 4th power. Now that's supposed to say x to the 4th. It didn't turn out quite so well. What do we do now? All right, well, let's see. Way back here, we introduced an identity that could potentially be helpful in a case like this. And here it is. Here it is. So actually, we can write this in a more general way. I have it listed on the next slide as a to the b equals e to the b log a. So what we're going to do here, because the function was if we think of this as a is 4 and b is x to the 4th, we could rewrite this as e to the b log a, which is 4. So how does that? Well, we have a rule for this one. And also keep in mind, this log 4 is simply a constant. So it's not quite as messy as it looks. If you think of this as e to the g of x is, you can think of this as log 4 times x to the 4th power. Then g prime of x wouldn't be that difficult. It would be 4 times log 4 x to the 3 power. And remember too that the derivative of e to the g of x is e g to the g of x, g prime of x. So where will that take us? That should give us e to the x to the 4th log 4 times 4 log 4 x cubed. I'm a mess, but that is the correct answer. Just double checking and making sure I didn't miss something. It's the original function, e to the x to the 4th log 4. The derivative of that would have to be 4 log 4 x cubed. Yeah, no, that's it. We're good. Now, this one. Well, of course, as we so often see that we can rearrange it algebraically. So which one is this? We may not need any of those specialty rules if we let u equal minus 3x. Let's see. Yes, we will. Sorry, we will definitely need one of the special rules because we do not end up with e to the u. We're going to end up with a to the u. So what we have here, I moved the 3 to the outside, of course. We have 3 integral to yeah, that's right. 2 raised to the u power. Now, what do we do with that one? Okay, so what we're going to need is the rule for the integral of a to the x power, which means we need this. Oh, you know what I just realized? We didn't actually have du here. Oh, yes, we do. It's negative. U is -3. Du dx is -3. Oh, you know what the problem is? Yeah, okay. This du requires a negative. So we need a negative here and here. All right, now we're good, but we need this negative here. All right. So in other words, we didn't actually have -3. We had to provide the negative ourselves. All right, now we're good. Okay, now once we have this in place, we have minus 3 integral of tu du. And according to what I'm seeing here, this should give me 1 over log 2 to the u plus c. And of course, we decided that u should equal negative 3x. So we end up with negative 3. I guess I can write that over the log 2. 2 to the minus 3x plus c. All right. Now, let's go on to part B. Now, here are some interesting applications of integration in practice: exponential growth and decay. Now, exponential growth means that you're looking at something like this. Some function increases at a very rapid rate. Let's say it would look something like that. And, you might run into that biology class. Remember when we talked about bacteria colonies and how quickly they grow, or if you're investing in something in finance where the growth rate is exponential, this could be the balance in your bank account, and decay would just be the opposite. Like, for example, the half-life of a radioactive isotope, something like that. So what we're going to do here is analyze some applications here, which do in fact involve exponential growth, among them being the growth of a population and the growth of the value of an investment. The decay, well, actually, there's a couple of good examples of this. It's the rate at which a radioactive isotope decays over time and reverts to lead or some other inert element. And you might remember from high school physics, this happens in, with, let's say, uranium or other radioactive elements. They don't stay radioactive forever. They continuously convert to a more stable isotope like lead. And also, everybody's familiar with carbon dating. The whole point of carbon dating is that it does decay at a certain rate, a very predictable rate. So in other words, if you wanted to know how old an ancient manuscript is, what you're looking for is the amount of carbon-14 that's present. And you can use that to work backwards to what date the book must have been produced, give or take. I mean, obviously it's not perfect, but it's pretty good. I mean, every crime show you've ever seen on TV, at some point, carbon dating is used to see if the evidence is the right age. Sometimes there's an interesting area. Well, there's a lot of interesting areas where this could be used, but one of them is in art fraud, where forgeries have been discovered because the canvases or the paints were not old enough to have been produced by the artist that supposedly painted them. And so, science is accelerating, and so it's getting harder and harder to fake art like that, because he might look right, but science doesn't lie, okay? So anyway, here's what an exponential function looks like. You've got some starting value or initial value, and then now the way we can interpret this, now this is obviously E, T is time, and then K is called the growth factor or growth constant. Okay, this determines how quickly the variable y is changing over time. And with the exponential decay, the only difference is that the exponent is negative. Okay. So if you want to see them side by side, this is decay and this is growth. Okay, they're the same except for the sign of the exponent. So here's a model that we can use to represent the growth of bacteria. Now, what I'd like to do is go into Symbol Lab and show you what this looks like. And you'll see that, as you would expect, it intersects the vertical axis at 200. and then it grows pretty fast. 200 times EXP, 0.02 times, call it X here. All right. Oh, it already kindly. Now, if you notice, the function itself is actually defined. The domain is the entire real number line, but for our purposes, we can only have positive values. This is t is time, so it can't be negative. And f of t is the amount of bacteria in the colony. That also can't be negative. So the only relevant part of this function is in the first quadrant, and you can see it starts at 200. That is our intercept. And after that, it grows quite rapidly. Okay, 2% per unit of time, basically. In this case, it's minutes. Okay, so that's what these numbers are telling me. So we could easily find out, for example, if I wanted to know how much bacteria there'll be after 5 hours, 300 minutes, well, you just literally plug in 300 for T, and you end up with 80,686. And you could also ask questions like this: how long will it take to reach 100,000? So now you're solving for T. Okay, so we're trying to figure out the appropriate value of T when the function is equal to 100,000. So you can see all you have to do is algebraically divide out both sides by the 200. So you've got 500 equals e to the 0.02t. Now, how do you solve for that? You take the natural log of both sides, because of course, as you know, the natural log of e to the x is just x. And that would be true for any base. So the way I solve for t is to take the natural log of both sides. So on the left-hand side, I have a constant log 500. On the right-hand side, I just have 0.02t. Now I multiply both sides by 50, or it divides by both sides by 0.02, which amounts to the same thing. And I end up with 311. Now remember, that's in minutes. So it's going to take a little bit over 5 hours to reach that point, which makes sense since we're at 80,000 after 5 minutes, 5 hours rather. Okay. Now here's a fun one. We're going to look at paintings and see how their value changes over time. We're going to look at 2 paintings. Okay, the first painting grows at a linear rate. It's worth $100,000 today, and the growth rate is estimated to be $2,000 per year. The second painting is also currently worth $100,000, but instead of growing at $2,000 a year, it grows at 2% per year. And that's a big difference, okay? Because every year, of course, 2% will be applied to a larger price, and therefore it'll grow more quickly than $2,000 a year. So the first painting's growth rate or value is a linear function. It starts at $100,000 today when t equals 0, and then it increases by $2,000 per year after that. It's a straight line. For this one, instead, it's 100,000 times e. The growth function, if you notice, the growth constant is 0.02, 2% per period of time, which in this case is years. It is clearly not a linear function. It is an exponential function. So if you plot these together, you can see what's going to happen. Now, this is taken from Excel. At first, they're growing very similarly. But this is painting A. This is the linear growth function, 2,000 per year. And the second one, this is B. This is the exponential growth. And what's happening is, of course, as time goes by, the spread between them is getting wider. So obviously, B proves to be a better investment than A. And as time elapses, the gap between them will get bigger and bigger. All right. Now, Often what we're interested in here is finding out what the growth rate is. In order to do that, we'll need to have observations at least two different points in time. So here's a wildlife example, believe it or not. Suppose that in 2006, 80 deer were introduced into wildlife refuge. And in 2012, the number had reached 180. Assuming exponential growth, what is the growth rate in this case? How fast is the population growing? So here what we have to do is let the year 2006 be replaced with t equals 0, and 2012 will be replaced with t equals 6. Okay, we don't want the years in the formula, it'll affect the results. Instead, we think of 2006 as the starting point, and 2012 is today, 6 years later. So we know what the populations are at both points in time. So we're going to write a slightly different exponential function here. We're going to call it n of t, n for number of deer. It doesn't matter what we call it. But you notice how the functional form is the same. Y0, the initial value, 80, e to the kt. Now, we know that n of 6 is 180. N of 0 is 80. This n of 0 is the same thing as y0. It's a constant. That's the starting point. We also have been told that when t is 6, we have 180 deer. So we are left with 180 equals 80 times e to the k times 6 power, where k is what we're solving for. So we divide out the 80 for both sides. Now what we're going to do is take the natural log of both sides. Okay, because the log of e to the x is just x. The log of e to the g of x is just g of x. So the natural log, this is just a constant. Oh, so all we have to do now is divide both sides by the 6. And we're all set. Whatever that number is, that is our annual growth rate. That's how fast the deer population is growing over this period. So you can see on the next slide, that works out to be approximately 13.52%. Actually, let me leave it there for a minute. It's approximately 13. Oh, whoops, I just realized that was supposed to be a K, not an X. I'm so used to X's. That's bad. So K, the growth rate, and as you'll see on the next slide, it's approximately 0.1352, which works out to 13.52% per year. Okay, that was that. So you can easily imagine, let's say, for example, you held stocks in a portfolio and you want to know, let's say, the value went from $100,000 to $1 million over 8 years. What growth rate did we experience, or what kind of rate of return does that represent? Then you can easily use this type of approach for that. All right. Oh, here's a fun one. A silver dollar minted in 1899 is now worth $37.42 to coin collectors. You could still, by the way, it's always valid. Any coin or note minted or produced in the United States is always legal tender. Yeah, I could take that dollar and spend it right now for $1, but I have to be foolish to do that because it's worth a lot more than that to coin collectors. Now, in some countries, like in England in particular, what they do is every so often they bring out a new design for the notes or the coins. And when they do, the old ones stop being legal tender. It's kind of surprising, which means that if you have them in your pocket, they're not worthless, but you have to take them to a bank and trade them for the new ones. I don't know why they do that. That's just the way it's done over there. But here, once it's been minted or produced, it's good forever. So this one is still good, but we're going to sell it to a collector for $37.42. What was the annual growth rate of the value of this coin? And here's a hint: in 1899, it was worth $1. Now it's worth $37.42, and that sounds like a lot of growth. But remember, it's been 120 years. So keep in mind that we're going to let 1899 be T0. That is the starting point. And then that implies that 2019 is year 120. Okay, so we're basically going to use the same formula that we had before, except this time it says V for value. It hardly matters what you call this thing. The main thing is that the functional form is the same. And the starting value, the Y0, is the initial value of the coin. Or if you want to, you can think of it as V of 0. That is 1 because it was a silver dollar. The time that we're interested in is 120 years. We know that the value at time 120 is 37.42. You can look at it on eBay, and there's your coin at 37.42. And now algebraically, we rearrange this. We don't really have to bother dividing both sides by 1, but we take the natural log of both sides, divide out the 120, and then it turns out to be approximately 0.0686, about 6.86% per year, which doesn't sound like a lot, but actually it is, because that means you're roughly doubling your money every 10 years. So it's actually very good. Imagine if your great grandparents had bought one of these and they left it to you in their will, it's worth a lot of money now, isn't it? Now we're going to look at money. Investing in the bank, because this is directly relevant. It's a perfect example of how you can use exponential functions in the real world. So we're going to introduce the concept of the future value of the sun, which means if you put money in the bank now, for any given amount of interest and time, how much will you have in the future? So we're going to use a formula, a very special formula, to figure this out. And here's what it looks like. So the way this thing works is that T is the present value. That's how much you started out with. A is the future value. R is the rate of interest, which would be expressed as an annual basis, so much per year. N is interesting. This is the number of what we're going to call compounding periods per year. And we'll get to that in a second. And then T is just the time measured in years. So given all this information, I can easily figure out how much I'll have in the bank in the future for any given investment today, based on the interest rate that I'm given, the time involved, and the compounding frequency. Let's talk about that right now. So remember, this is a bank. You're putting your money in the bank. You leave it there, you get interest. The bank, in the meantime, is lending your money out to other customers at a higher rate of interest, and that's how they make their money. The compounding frequency refers to the number of times per year that interest is credited to a saver's account. Now, it's possible that the bank just waits to the end of the year and gives you the money all at once, but that's not normally the way it works. So I have a chart here which shows some of the possibilities. For example, if they paid you interest twice a year, let's say halfway through the year, they figure out how much your balance is, and they give you 6 months worth of interest, and then they do the same thing at the end of the year, that would be considered semi-annual compounding. If they do this every month, that is defined as monthly compounding. And if they do this every day, this is defined as daily compounding. Now, obviously, when they do it more often, they don't pay you the full year's interest all at once. For example, with semi-annual, they give you half the annual rate of interest twice a year. Here you're getting a 12th of the annual interest 12 times a year. And here you're getting 1/365th worth of the yearly interest every single day. In practice, most banks use what we call daily compounding. That's the norm. Okay. Now, that's actually going to help you if you're the saver. It's going to harm you if you're the borrower, because that means that there will be more interest involved. All right, so let's look at a couple of quick examples here. Imagine somebody borrows $10,000 for 3 years. The rate of interest is 6%, but the interest is compounded monthly, which means they're being charged 1/12 of 6% or 0.5% every month. How much interest will you pay during the lifetime of that loan? Well, that's what this formula will tell us. Okay, first it'll tell us how much we're paying back. And when you subtract the principal, whatever's left over must be your interest. Okay, so these are the variables. Principal, we borrow 10,000, 6% per year, 3 years, 12 times a year, the interest is compounded. So if you plug all those in and take out your calculator and do this. By the way, here's a helpful hint. You probably will want to simplify this first. Or what I mean here is, let's say you take this and rewrite it as 1 plus 0.5%. And your exponent would be 36. On the calculator, you probably would want to do this in the following way. Do this part first. Now, on the TI-84, the exponentiation key is this thing, the caret. These are the steps you would follow. 1,005 raised to the 36th power comes first. If you go from right to left, the advantage of doing it this way is that you can avoid the need for a lot of parentheses, which isn't a problem. It's just that I think it's easier to avoid mistakes this way. So if you do it this way, you will in fact end up with 1199.6681 after rounding to dollars and cents. Now, since your original principal was $10,000, whatever's left over must be the interest that you paid, because you're paid more than you started out with. You borrowed $10,000 and you end up paying 1199.6681. That implies that the rest is interest. Okay, now the next example gives us an opportunity to practice with this concept with different assumptions about the compounding frequency. We're going to start with $1,000, deposit it in a 1-year bank account. It pays a rate of 4% per year. And we're going to assume 4 different compounding frequencies, first annually, semi-annually, monthly, and then daily. Which implies, this is 1. This is 2. Semi-annually means twice a year. Monthly is 12 times a year, of course. And then daily is 365. So in the formula that we're using, the only thing that changes in each case is n. Okay. So when we're done, we're going to not only have some good practice, but it'll illustrate an important point. So remember, P is 1,000. We started with 1,000 in the bank, a 4% rate of interest per year for 1 year. Let's plug everything in case the first case when n is 1. Should we go through all the steps? Now, by the way, it should be clear then that you must have earned $40 worth of interest in this case. Okay. Now, for the part B, when we have n equals 2, I'm going to change 2 things. I'm going to have 2% twice a year instead of 4% once a year. So let's see how much of a difference that makes, if any. So when you change it, and by the way, on the calculator, what you're actually doing then is this 1000 times 1.02 squared. And oh, look, all of a sudden we have this extra 40 cents. It's not much, but it's still 40 cents. That's your money. Okay. So you'll take it. Now let's move this up to 12 times a year. And again, the only thing that's different is here. I'm going to get 1/3%, but 12 times a year. And if you plug that in, so 0.04 divided by 12. Yeah, it's not an even amount. It's 0.00 and then a string of threes raised to the 12th power. And you'll end up here. And of course, this implies that the interest is $40.74. So you notice what's happening here is that every time I increase the compounding frequency, the interest is going up. And if I do this on a daily basis, it goes up a little bit further, but not a whole lot. The interest here is $40.80.8. So compared to daily, monthly rather, it only went up another 6.8 cents. Now, in practice, the compounding frequency doesn't go beyond daily, but there's really nothing to stop it from becoming more frequency. In other words, there's nothing to prevent the banks from doing this every hour or every minute or every second. In the limit, imagine yourself taking the limit of this expression as n goes to infinity. This is what we're building up to. The limit as n goes to infinity is something called continuous compounding. And you'll see that when we reach this point, we are experiencing exponential growth. That's what this has been all about. This is an example of exponential growth. And in fact, I'm going to show you the limit on the next page, and you'll see exactly what I mean. Oh yeah, that should look familiar. PE to the RT power. It's an exponential growth function. Okay, so remember, we started out by saying that an exponential growth function looks like this. Okay, well, that's what we have here. It's actually A now, though. So when interest is compounded continuously, it's called, meaning an infinite number of times per year, then the balance in our account will grow at an exponential rate. So that means that if you plot it out over time, just like the painting, remember before we saw the painting that's growing at an exponential rate? It's the same thing. Now, what's interesting, though, is that compared to daily compounding, the increase isn't very considerable. I mean, remember before it was 1040.808 approximately. The difference here wasn't that considerable, but it's not zero either. This is the limiting case. And in fact, if you were to plot out all the different compounding frequencies, let's say this is your future value A, and this is the compounding frequency. This result that we just got would be the asymptote of this function, 1040.810774. That's the asymptote that it's converging to, but never quite reaching. So this is a classic real-world example of exponential growth. Now in practice, we don't quite reach that, but the daily compounding, we're getting very close to exponential growth. So the balance in your account with daily compounding will very much resemble this graph, at least over a long period of time. It'll take a while before it starts to rise very quickly, but once it gets going, you can see that if you save money for 20, 30 years, it'll grow very, very quickly. Now, continuous decay is just the reverse, as we discussed. we can use the same notation here, except now we can think of this. There's a few things that we could apply this to. You could apply this to the value of a new car, let's say, where it experiences depreciation. But why don't we stick with the classic physics example of radioactive decay? We have radioactive element decays at a rate of 5% per day, which means it's being converted to lead. Or if you want to think about it in terms of carbon-14 dating, we can do the same thing. If I had the exact numbers here, we could figure out how old something is with carbon dating. But anyway, let's just assume that we start with 100 grams of the radioactive element. After 10 days, if this function is correct, you can see, well, 5% a day is a very rapid fall off. After 10 days, we're only going to have about 6.0653 grams of radioactive material. The rest is lead. Okay. There you go. How about this example? Now, here's something interesting. This can come in very handy sometimes. If a variable grows exponentially, let's say the balance in your bank account, we can easily figure out how long does it take to double your money. Oh, so like, let's say the bank pays you 6%. And you're being paid, let's say the bank really does use continuous compounding. Okay, hold on 1 second. According to this, it's about 11 and a half years to double your money, right? So very handy little formula to have around. I think you'll agree. And again, even if you only have daily compounding, you're close enough that that's going to give you a good approximation. Or how about this one, a population example? You've got fish in your local lake where you go fishing, and initially there's 500 fish in the pond. And we discover that 6 months later there's 1,000. When will the population reach 10,000? So this time we're not being given the growth rate. Instead, what we're being given is the value of the population at 2 different points in time. So what are we supposed to do about that? Well, the way to think about it is that log 2 over k is the doubling time. Here, the fish population doubled after 6 months or half a year. So that means that we can set this expression equal to 0.5 because it took 6 months. To double the population. So we're basically working this backwards now. Now we're going to figure out what the implied growth rate is. So algebraically, of course, we're just going to solve for k. We'll have a half of k is log 2. All right. Let's get that. Log 2. Divided by a half. Oh, 138, 1.386. 138.6% is the annual growth rate in the population, which makes sense because, I mean, it took less than a year to double the population. So the growth rate is pretty high, 138.6%. And in order to figure out when the population reaches 10,000, we have this formula now. This is the initial population. And which is 500, of course. we're asking when does it reach 10,000? We're solving for the time at which population reaches 10,000. So algebraically, now remember, so first divide out both sides by the 500. You've got 20 equals e to the 1.386t. Take the natural log of both sides. You've got log 20 is 1.386. Obviously, then we're going to divide by 1.386. And that ends up being about, as you can see in the next slide, 2.16 years. So those fish are really growing. They must be getting fed very, very well. Or maybe it's a koi pond where they're being fed very exotic foods. Now, what's interesting here is that this formula lets us know how long it takes to double some value. We can also use it to determine the half-life. But K now, instead of being a growth rate, it's a decay rate. Okay, that's the key though. This is now a decay rate. This is how it shrinks over time. So if we have, oh, here we go. We finally get to do carbon-14. The half-life of the isotope carbon-14 is 5730 years, which means that after 5730 years, half of it has been reverted to nitrogen-14, which is a completely non-radioactive element. And it's decaying at an exponential rate. Okay, so we know this from experience. So therefore, how a substance that contains 100 grams of carbon-14, how much will be left in 50 years? Well, we know that 5730 is how long it takes to cut our radioactive carbon-14 in half. So we set that equal to this expression and solve for K, and that's 0.000121. What do we do with this? Now, this, remember, is the growth factor that we're just solved for in the exponential decay function. So what we can do now is say, well, listen, if we started out with 100 grams of carbon-14, how many would remain after 50 years? Okay, so in other words, if let's say for some reason we know that when this thing is brand new, it contains 100 grams of carbon-14, this implies that after 50 years, it will be down to 99.4. Or we can work it backwards and figure out what the carbon-14 must have been 100 years ago, or else how long ago it was at 100. So we can figure out a lot of useful information here. Here's an interesting one. So let's say that we do have an artifact that originally contained 100 grams of carbon-14. It's now down to 10. How old is the artifact? Well, given the exponential rate of decay that we just calculated, we plug that in. So we start with 100. Okay, carbon-14. Remember, carbon itself, the atom carbon has an atomic number of 12. This is an isotope that takes on 2 more neutrons. So anyway, 10 is where we are now. So after doing some algebra, of course, taking the log of both sides. Now, this is interesting. According to this artifact is 19,000 years old. So this is something from ancient Egypt or something like that, or even older than that. Yeah, ancient Egypt, the pyramids are only about 6,000 years old. So this is going way, way, way back. This is like cavemen days. The cave paintings in southern France, for example, might be 19,000 years old. But anyway, so these are all applications of exponential and functions where we have growth and decay. So I hope you found that interesting. So we're now completely done with chapter 6, and that means we're done with the course. So what remains to be done is to finish up all the assignments, and then you'll be ready for Calc 2. Now in Calc 2, you're going to do a lot more advanced integration, among other things. So it's important that all this background be in place, but a huge percentage of the time in Calc 2 you'll be spending on integration and all the different techniques. There's a lot of them. You've only been exposed to one or two of them so far. Actually, the most important ones you've seen so far is the U substitution and the power rule, but it gets very messy very quickly. So you learn a lot of cool new techniques, and then more important other applications that will get you ready for Calc 3, and then any other math courses you choose to take. So hopefully this course was good for you. You learned a lot, and then you also saw some interesting applications. And who knows, maybe I'll see you in Calc 2 next summer. So all right, have a good day.